Fantastic. Good evening, and thank you for attending the 2013 CyDrone CDR. CyDrone is a multidisciplinary, student-driven group project dedicated to designing, manufacturing, and operating low-cost, small, unmanned aerial vehicles capable of performing a variety of civil applications. Now for some brief introductions. My name is Adam Kaplan, and I'm a senior in aerospace engineering.
I'm Ted Harden. I'm a junior in aerospace engineering.
I'm Alex Woodholm. I'm a freshman in aerospace engineering.
I'm Zachary Lamy, and I'm a freshman in aerospace engineering.
I'm Michael Phillips. I'm a junior in aerospace engineering.
I'm Logan Butler, and I am a senior in aerospace engineering.
I'm Will Bryan, and I'm a computer engineer.
I'm George Falscraft. I'm a senior in aerospace engineering. I'm Justin Logan. I'm a sophomore in chemical engineering.
Over the course of today's presentation, we'll discuss the project's background. We'll touch on our current program, which is CyDrone X3. We'll go over some materials testing, some further testing analysis we've done on various other subjects, and we'll conclude with an outlook. So with that, we'll go ahead and get started with the background. In 2004, NASA DRIVE released a list of issues preventing UAVs from being more widely used in the civil airspace. CyDrone focuses on three of these issues: affordability, payload flexibility, and operator training issues, which we hope to solve through increased ease of use. Our very first iteration, CyDrone X1, was out of the gate affordable. However, due to its balsa wood and monocode construction as well as its conventional landing gear, it was not easy to use, nor did it offer the payload flexibility the project sought. Our second iteration, CyDrone X2, increased the ease of use by basing itself around the Multiplex Easy Star, an EPO-built, hand-launched controlled crash landing aircraft. It maintained the affordability of CyDrone X1, however, it did not increase the payload flexibility. At this time, the team determined that the only way in order to accomplish all three goals would be to build our own aircraft. And so for that reason, we began development on CyDrone X3. CyDrone X3 aims to be simultaneously affordable, easy to use, and will offer significant payload flexibility. This will be done through the use of two separate payloads. The upper payload is the FCS, the Flight Critical Systems box. This contains the transmitters, the receivers, the autopilot, all of the essential components that truly make this airplane a semi-intelligent UAV. The lower payload is the module, or the mission pack. This contains specific items suited to the mission that the aircraft is currently being used for, such as an HD imaging module or an infrared camera. These payloads can be accessed through a quarter-turn nose cone, which attaches to the fuselage. Furthermore, the wings can be removed from the aircraft for ease of transport. Now with that, I'll go ahead and hand it off to Ted, Alex, and Zach for more on CyDrone X3.
So during the design process of X3, we had to make some late-game modifications. For example, with our ABS-like 3D printed nose cone, we actually had to thicken up some of the edges to that to make sure it would resist braking. Also, we enabled the nose cone to hold our vertical antennas. Also, the way our fuselage and wing fit together didn't allow us to actually use the automated processes we had available to us to make these separate components. So we switched the way in which they interfaced. So basically, we added some of the airfoil geometry onto the fuselage so they could fit together easily.
To properly align the FCS module, we designed foam inserts. These have been manufactured out of EPS and will be glued into the internal rigid structures too.
Also, the tail configuration for CyDrone X3 did not give us as good of rudder and elevator authority as we wanted, so we decided to enlarge these surfaces to give us better rudder and elevator authority.
We created a more detailed model of our flight critical systems that accurately shows the layout of our SDS. We can also use the components and wires from this model as a guide for future designs and models.
At the beginning of this semester, we estimated the X3 to be about 3 kilograms. After a reevaluation of the SolidWorks model, we figured out that it's actually 2.5 kilograms. The SolidWorks model also showed that the center of gravity is exactly where we designed the wing spar to be, taking most of the load of the airplane.
So here is the design we're shooting for X3. And here are all the components we currently have manufactured and in hand, being ready to assemble. So here's a few pictures of some of the physical components themselves. Here's our ABS fuselage and nose cone, as well as some of our carbon fiber support spars. Here are some of our blue core CNC components, for example, our tail boot, our tail configuration, and as well as our nose cone. Here's our tail configuration put together. We haven't adhered anything together yet because we still have to do some detail work, for example, cutting out some of the control surfaces. So now we're going to move on to X3 not manufacturing flight tests. So a lot of these automated processes, for example, 3D foam cutter, the 3D printer, as well as our CNC machine, take a long time to complete. There's a lot of people in the queue. So instead of just waiting for X3, we decided to validate our aerodynamic performance analysis with X3 not. With the help of Laser, we built this model that is as close to X3 as possible. Everything you see on the slide is handmade except for the wing pieces. So since the materials for X3 Naught is slightly different than X3, we actually had to add a little bit of mass to the front of the fuselage. This was 1 kilogram weight. This moved the CG to a better position, closer to the X3's center of gravity, as well as increased our weight to 2.7 kilograms, which is very close to our weight estimate. X3 Naught performed a series of successful flight tests. Here are a few of the pictures from those flight tests. And here's our flight testing program. Basically, the first series of flight tests were conducted to test our basic flight characteristics, and our second flight test was to acquire data with our electronic components as well as test the critical flight performance. Unfortunately, during this critical flight performance test, some of the aircraft components were damaged during transport, and we had to abort the test flight early. But we're still able to get a lot of data from this. In blue, we have our throttle control input, and in green, we have our altitude. We can extrapolate a lot of flight data from this. So now I'll hand it over to Michael for material study and count.
All right, so since we had to reprint our nose cone, we decided we wanted to make sure we were using the best material possible. So we got 3 suggestions from the 3D printing company representative. One was a hard plastic, another was a hard plastic and a soft plastic mix, and the third was an ABS-like plastic, which is the plastic we're currently using. So a stress analysis was done in SolidWorks, where we applied a 9G load to the bottom half of the cage. And basically the stress in this picture is going to be the same for all the materials because there's no plastic deformation. With that being said, we started off with the Vero Gray, which is the mixture of the soft and hard plastic. It provided a displacement of approximately 3.75. The Vero White, which is the hard plastic, provided a displacement of approximately 3 millimeters. And then finally the ABS-like plastic, which is what we are currently using, provided a displacement of approximately 2.6 millimeters. Therefore, based on these testings, we decided to go with the ABS-like plastic, which is what we chose in the first place, but we wanted to make sure we had picked the best material. We chose this because it provided the least displacement, and it also has a really high elongation at break. One issue we could run into is the way that the 3D printer works is it lays down the material in sheets, and so the shear strength in that plane is going to be less than optimal. So we need to keep that in mind in the future. Now we'll be on to Logan with more material testing.
So X3 was originally designed to use a skin made out of expanded polypropylene foam. It is very durable and very lightweight. However, in our testing with the machine, the surface finish is very rough and just not suitable for what we're wanting. So we decided to use an expanded polystyrene foam, which is much less durable, so we needed some way to protect it. The first product we were looking at was fiberglass. It is very heavy, and it's just not quite cost-effective, even though it's very strong. So we started looking at other commercial products, such as Plastidip. Now, in our initial testing, we saw that it melts foam really well. It also adheres very poorly to the foam at hand. A fingernail can pull it all up. It also melts foam really, really well. And it is applied in extremely thin layers, which is not representative of how they advertised it. So we will not be using Plastidip on our foam plane. So the second product we're looking at right now is called StyroSpray. It is very strong and it is very flexible. The only issue that we have is that it shrinks slightly while curing. This can be alleviated by putting some sort of a primer or epoxy underneath of it to pull on that rather than the foam. And we will be doing some impact testing in the near future. So now I'm going to hand it off to George and Will to talk about our ground station.
CyDrone uses high-gain antennas to achieve long range and increase the signaling quality without an increase in transmission power. This semester we redesigned the ground station to improve panning capabilities and prevent wire binding while panning. To do this, we moved the servo from the base of the assembly into the assembly itself and adjusted the antenna array to accommodate the servo. Will with electronics.
In conjunction with our antenna tracking hardware, we are using an open source community-driven piece of software called the ArcticPilot Mega Mission Planner. And we use this to communicate or facilitate communication with CyDrone, log the data from the flight, and control the antenna tracker itself. Over the course of the semester, we've made a couple changes, the first of which is the protocol used to control the panning and tilting servos. Previously, the protocol used didn't give us quite the precision or accuracy that we were looking for, so we scrapped that protocol and implemented a new one, giving us much better precision and accuracy. The second change that we made was in the AVR writer, which allows us to create a video of our forward-facing video overlaid with the heads-up display information. it previously didn't work. The video output did not work in all media players. So we made a change that makes it more universal and more closely adheres to our ease of use principle. Now Justin's going to talk about it.
Up to this point, our presentation has focused on the design and manufacturing of our platform, and now I'd like to talk briefly about our optical payload and image processing. Here is a list of requirements that our camera setup needs to meet. Our biggest obstacle was finding a camera that will allow us to do continuous shooting without physically holding down the shutter release. This led us to CHDK. Canon Hack Development Kit is a firmware enhancement for all Canon PowerShot cameras and allows the user to control every aspect of the camera. With CHDK, we are able to write scripts executable directly from the camera so that we can do continuous shooting. Because of this, we've chosen the A23 as our camera setup. It is extremely affordable and it meets all of our requirements. Here's a comparison of two photos taken with and without CHDK. Notice the shutter speed on the right picture. It has very fast shutter speed, which allows us to eliminate blurring due to unsteady flight. Now, the standard would be for us to create a panorama with the shots that we capture, but we would like to take it a step further. Orthorectification is the process of creating a three-dimensional mesh from similar features by comparing overlapping photos. Here are a list of software programs we've been looking into. We've been getting great results, but we have not chosen one yet. Here's an example using 123D Catch. Notice when viewing from different angles, you're able to see both sides of the wall. While X3 is in manufacturing, we would like to test our camera setup right now, so we've decided to go with the Fin-Wing Penguin as our test bed. It has ample payload capacity and an airframe dedicated for aerial photography. I will now pass it on to Alex and Zach for design tips.
Presently, X3 is made out of blue core foam, and we approximate the weight to be 2.5 kilograms. If we add styro spray to the leading and trailing edges and the parts that will get rigorous abuse, it will weigh approximately 3 kilograms. However, we believe we can make this even lighter, so we started an X3B study.
And with the X3B, changing blue core components to EPS and also removing the internal rigid structure will save us about 1 kilogram of mass. This will allow us to apply more styro spray and create more of an exoskeleton structure. Now on to Michael with the X4 study.
So learning from X3, we decided that we wanted to cut out as much mass as possible. By doing that, we would save about 600 grams by cutting out the rigid structure from the fuselage. We also want to optimize the amount of volume in the fuselage, and we want to start by designing from the inside out, which we learned works really well from X3. We also saw in X3 that the vertical stacking of the FCS and module box was really space inefficient. We didn't have as much volume in our module as we wanted, so we decided to go with a horizontal stacking. The next issue was how we were going to load the FCS and module into the aircraft. Would be we could do a top loading feature or a front loading feature. The issue with the front loading feature is we'd have to cut a chunk off the nose cone, and then it would be exposed to elements, and it also lacked accessibility for the electronics. Here you can see a picture of the X3 fuselage and the current module payload size that we have to work with. And on the right-hand side is the new X4 module. It has a lot more volume, and it still has the same fuselage size as the current X3. I will pass it on to Adam with the outlook.
Okay, so now I get to bore you guys to death for about the remaining minute of the presentation. At this point in time, CyDrone is doing very well in the funding sense. We were initially given funding approximately $2,600. We've expended about $550, leaving us with approximately $2,000 remaining. We do not anticipate any large expenditures moving forward, but we will, of course, keep you guys updated as we move on. Now for the outlook. Of course, for the rest of the semester, we'd like to actually assemble CyDrone X3 and begin ground testing and hopefully some flight testing. While this is occurring, we can continue to push forward with the X3 Not Flight Test program to gain a greater understanding of the aerodynamics of X3. We'll continue testing both our materials and our ground station, and we will also continue to develop an optical payload, and we'll be continuing our design studies. So let's take this opportunity to offer some special thanks. Thank you first and foremost to Make to Innovate, Matt, Jim, and Bill, who's not here for some reason. Really looking forward to seeing him. I cannot thank you guys enough for all the time you put into this. I'd like to thank Boeing for their very generous donation that helps make everything possible here. Special thanks go out to another Make to Innovate Team Laser for their assistance in constructing X3 Not, as well as the flight test program. I'd like to thank DIY Drones for the Autopilot Mission Planner. And certainly, not least, we'd like to thank the Aerospace Engineering Department for helping to facilitate all of these fantastic things we've been able to do. So at this time, we have reached the conclusion of our presentation. Thank you very much for attending, and we'd be happy to answer any questions you have at this time.
Going back to the components of the job, you said you're about 9 years learning through it. Is that something you can expect in regular life, or that just needs to be in case?
That's just general practice of you design something for a 9G crash. No, we don't expect to have any 9G crashes. If we were designing stuff for a 9G crash, we would be making stuff a lot bigger and a lot more bulky. Well, actually, technically, we would be keeping it the same, but we aren't expecting that, I guess. That's what I'm saying.
We can only make it so easy to use.
Exactly.
What kind of flight time are you guys anticipating? 32 minutes? Okay. 42. Oh, okay.
Now, it's worth noting that this analysis was run previously when the weight was predicted to be either 3 or 3.2 kilo. So, 3.2 kilo. So we're hoping to pick up a few minutes. Actually, this is something we're actually looking to test with X3, not just fly it in circuit with a voltage current sensor on board so we can watch how it performs. Sure.
Okay. How about the range?
Well, the range is mainly constrained by gravitational moment. So,
cool. Okay, so basically we intend to operate this, think of a circle. The midpoint being the ground station where you've got a radial range. Per the radials, we can give you approximately 5 mile or 8 kilometer, roughly the same there. Linear distance, if you're going to fly the airplane from point A to point B and ignore radial range, I think we were hitting something like 12 miles. So we've got room to hit.
Well, our cruising speed is approximately 19 knots, so basically 19 times 42 or 60.
In any event, though, certainly more than it would take to reach the edge of our radial range in return.
Have you done a power analysis as far as like what's your biggest drain of power? I mean, I assume it's the engine, then you
Absolutely.
Electronics.
No, you're absolutely correct. The engine is the main consumer of power. This is all budgeted out. I don't have it in the presentation. I don't remember the numbers verbatim, but you're dead on. The engine is the #1 consumer.
Of the extra stuff, I mean, how much do you have budgeted for use by your payload and cameras and sort of stuff versus like how much do you have for radio?
Good question. At this point, let's see if I can get forward again so you can see the interface. So it'll take me just a few seconds, I promise. Okay, a few more seconds. There we go. Okay, so we've got the interconnector up top as well as down below in the module. So ideally, we'd like the modules to be self-powered. This would be one of the fantastic things about the GoPros, or in this case, the Canon. We don't need to supply external power to it. So at this time, we've really not budgeted all that much for supplying power to modules that we haven't out designed yet. But because we don't anticipate that someone's really going to need to operate at the lengths or for the time that we're allowing, we should have more than enough power.
How many more test flights are you guys anticipating to do yet this semester? I know you got a couple in, but...
Well, basically, as I mentioned before, we damaged certain parts of X2 not transportation. So before we conduct any flight tests, we actually want to smooth out the way we transport it.
Okay.
Basically, since we have 2.5 feet wingspan, so putting that in the back of the truck bed, not very well supported. So I would say we'd probably be able to, like, for sure, test our critical flight performance towards the end of the semester. We have to do something before that.
Okay. And beyond that, we'd also like to do that circuit flight so we can get a better feel for how our endurance calculations stack up.
Okay. Is that including doing a test flight for USDA?
That's actually going to be through the X2C platform.
X2C, okay.
While all of this testing is going on, we want something that we know will work because it's really focused more or less on the payload.
Okay. Good. Any other questions?
Anyone online?
I don't see any. Do you guys see any online? No? Okay.
You guys have any questions? I'll figure it out.
All right. If there are no other questions, then very good. Thank you very much.
Thank you. Okay.